Alright, so far we've been looking at projectile motion or objects flying through the air with no drag force, no force due to the friction of an object moving through a fluid. So a fluid is anything that can flow, like a gas or a liquid, and if that fluid is not moving at the same rate as some mass, maybe we have a bullet and here's our fluid. This is our air that the bullet's traveling through. Put some rifling on there. If there's a difference in speed, so the velocity of air is different than the velocity of the bullet, then we have what's called a drag force. It's going to go in the opposite direction of motion. So use F sub D. I think your book uses a capital D. Either works. But if our motion was going to the right, the force of drag is going to work exactly in the opposite direction, slowing us down or impeding our motion. And we'll see that it's a function of velocity, and not just that, it's a function of velocity squared. So just a couple quick things. This works for anything moving through a fluid and any type of shape. There's ways to calculate what's called the coefficient of drag based on the shape of the object. There's a table in the book that gives you coefficients of drag. What is the coefficient of drag? Well, let's figure out what the formula for our force is. So this impeding force of viscous friction, right? It's a fluid frictional force, is equal to 1/2 times a constant c, that's our coefficient of drag, times rho, which is the density of air. So right now you can probably tell that the force of drag is different at different altitudes. As we get further off the Earth's surface, we eventually get into space, right? And as we get higher and higher, the air is thinner and thinner. So we would have less drag at high altitudes. We can travel at much faster speeds at high altitudes. Remember, like the space shuttle, the little lander comes in, or it hits the atmosphere and starts burning up. It can handle that burn, but it gets very hot. That is all due to the frictional force. Remember, friction is non-conservative. It's a non-conservative force. And the reason being is it turns into heat. It turns into light. It turns into sound. It turns into things we can't turn back into motion, right? You might not think friction creates light. It does. It produces some level of infrared due to the heat. It also there's a sound. Sound is actually energy. If you're losing energy to something like sound or heat, we cannot turn that back into mechanical energy. And we'll learn all about that in the next unit. I just like giving you a heads up. And this is mainly to point out friction is non-conservative, and so is the force of drag. So let's finish this formula. The force of drag is 1/2 times the coefficient of drag for that object, so it's object specific. And we multiply that by the density of air, so that depends where we are on the Earth's surface. If we're in a very humid environment, that's going to change versus being in the desert, right? We have more moisture in the air, and therefore the air is more dense. And we multiply that by the cross-sectional area of the device of the object that is going through the air, or fluid, doesn't have to be air. And then it's all multiplied by the speed squared. It always acts in the opposite direction, kind of like Hooke's law does, right? Same like just think of it like friction, right? Friction always opposes motion. Always. 2 P's? I don't know. It always opposes motion, and drag is friction. It is just fluid friction. Okay, so let's take a look at what this coefficient can be. I want to do some unit analysis. Before that, point out this is pretty big that it's a function of the velocity squared, and you may have noticed that in your car. If you're going 30, 40 miles an hour, there's not much drag on your car at all. If you put your hand out the window, it doesn't get thrown back from the drag force of the wind on your hand. As you start getting to like 70, 80 miles per hour, depending on what kind of vehicle you drive, or regardless of what kind of vehicle, you have the drag force as a function of v squared. So as your velocity goes up, the drag force goes up as a function of v squared. It goes up pretty drastically. So there's a lot more drag on your car at 100 miles per hour. So the force of drag at 100 miles per hour is much greater than the force of drag at even 80 miles per hour. Right? Square the two numbers and see what the difference is, or take the ratio. Recognizing what things are truly functions of. So in this case, it's a function of velocity squared. That tells you a lot of information about this force. Let's do some unit analysis though. Let me copy it down real quick one more time. I have the force of drag is equal to 1/2 times the coefficient of drag times the density of air times the cross-sectional area times the speed squared. Alright, let's do unit analysis on this. Figure out what units C has. Okay, let's go ahead and just call the force of drag a Newton for right now. Let's see what all this other stuff turns out to for now. We drop the 1/2 when we do unit analysis, so don't worry about it, but we still need to hold on to that C. Now, rho has dimensions. This is our density of the air, and density has units of kilogram per meter cubed. We're going to multiply that all by the area of anything, cross-sectional area, has units of meters squared. And velocity squared would give us meters squared per second squared. Alright, it looks to me like we should go ahead and use the Newton definition of kilogram meter per second squared. That'll help us cancel some stuff out. Copy all this back down. I can combine my m's. This is m to the 4th over m to the 3rd. So I get just m on top. And I get a 1/2 squared. Okay, well, we can start, excuse me, canceling. We have a kilogram on both sides, we have a meter on both sides, and we have a per second squared on both sides. The fact that this comes out to equal 0 doesn't mean it's equal to 0 in this case during unit analysis. It just means that this is a dimensionless unit. And you'll come across quite a few of those in your time. Now, like the capital G for gravity is not dimensionless. Planck's constant, which you'll see in your future is not a dimensionless unit. So far, this right here, the force of drag, or the coefficient of drag, is unitless, and we've had one other one. The force of friction was equal to mu times the normal force. The coefficient mu was also unitless. What kind of values does C have? There's a table in your book, but typically ranges from about 0.4 to 1. The interesting stuff in the table is that it tells you the terminal distance of objects, or the terminal speed, sorry, terminal speed. What is terminal speed? Well, if we have an object, let's just say we have a mass, and the only force acting on it is mass times the acceleration due to gravity, and we also have some drag. We get terminal speed when the acceleration goes to 0. Basically, if we've released it from rest, it's going to speed up, get further and further away, right? And eventually it's going to reach some maximum speed. So terminal means end, but in this case it's like a maximum speed. It can't speed up anymore. It reaches a point where the acceleration is 0, and then acceleration is 0 because the force of drag ends up having the same exact magnitude as the weight. So what we can do is imagine a couple scenarios. Let's say we start at rest and we have this mass. All that's acting on it is mass times gravity. Now let's say we drop it and look at it a couple seconds later, let's say 1 second later. At this time it is now still having the force of gravity acting on it, but it's got some drag, and if it's shortly after released, unless it's like a parachute or something, it's still going to be speeding up. The acceleration will be greater than 0, and the reason it has an acceleration is because the weight, this length is bigger than this length. So the forces are unbalanced and there's more force pointing downwards, speeding us up in the negative direction. So speeding up downwards. Alright, if we looked at something, I don't know how long it takes. We can calculate that, but let's just say at terminal velocity. We looked at rest, we looked at shortly after releasing the object, and if we look at terminal velocity, when it can no longer go any faster due to its shape, due to the density of air, that literally means that the acceleration is now 0. It cannot speed up anymore. So if we look at a free body diagram on this, this is going to occur when the two forces acting on the body, the force of drag and the weight, are exactly the same length and pointed in equal but opposite directions. So what do we get if we analyze this? Our free body diagram would say that the force of drag going up minus mg going down is going to be equal to this mass times the acceleration. And in this case, if we let the acceleration go to 0, we're saying that the force of drag is equal to the weight, mg. So that is what terminal velocity is. The forces are balanced and the acceleration becomes 0. At that point, you're actually only going to go slower and slower, because as you approach Earth, the air gets thicker and thicker. It becomes more dense. So you'll actually lose speed as you get closer to Earth, just for that reason. If we wanted to find what the terminal speed of something is, terminal velocity, how would we do that? Well, let's use the formula that we found to calculate drag, and let's also use this right here. So I have the force of drag minus mg is equal to the mass times the acceleration, and we said for terminal velocity the acceleration has to equal 0. Okay, well, let's take that and let's substitute in our formula for the force of drag. We have 1/2 times the coefficient of drag times the density of air times the cross-sectional area times the velocity squared. And we can throw this on the other side and say that's all equal to mg. Now we can solve this for the velocity, and doing so would give us the square root of 2 times mg, or the force of gravity, all divided by the coefficient of drag times the density of air times the cross-sectional area. So if you know these conditions right here and want to know how fast something can fall, then this is how we would do it. A problem may give you a terminal velocity and ask you what the coefficient is, or what the cross-sectional area is, or maybe what the density of air is in that specific area. They would have to give us everything but one of those, but we could still solve for it. And check this out. We've noticed so far that as things fall in a vacuum, mass didn't matter. And we'll see that more when we do energy methods. The speed right before something hit the ground, right, v final, was not a function of something's mass at all. If it had some, right, it's our kinematic formulas. If we wanted to find the velocity after it fell some delta y, it's v final squared is equal to v naught squared plus 2 times the acceleration due to gravity times delta y. And I could find that. And this has no mass anywhere. Mass doesn't matter. But now once we introduce the force of drag, it does. Okay, so mass is actually in the solution. See if there's any pointers on this other than that. Basically, when you release something from rest, the force of drag is equal to 0. As it speeds up, so these are just different time periods, it always has mg pointed down, but it might just have, well, initially it would have no. In its next instant, it just has a little bit of drag. And it's going to continue growing as it speeds up until they're equal. Once they are equal in magnitude, then we get what's called terminal velocity. Alright.